gas law portion of your chemistry course. To start off, let's look at an example of the type of problem you will find during this section. Calculate the volume that 0.65 moles of NH3 gas occupies at 37 degrees Celsius and 575 torr. All right, now in this problem, they've given us lots of things. They've given us moles, pressure, temperature, and they want us to find the volume. We have a formula. This formula is called the ideal gas law. PV equals nRT, where P is pressure, V is volume, N is the number of moles, R is the ideal gas constant, and T is temperature in Kelvin. This formula is actually a combination of three other gas laws: Boyles Law, Charles' Law, and Gay-Lussac's law, also known as Avogadro's law. Now, Boyle came up with a hypothesis of how pressure would relate to volume if the temperature and the number of molecules of gas remain constant. Boyle hypothesized that if volume increases, pressure decreases. Now let's think about if this makes sense. All right, let's say we have a box, and inside that box are a bunch of molecules floating around. Let's say we have 4 little atoms or molecules. And now let's expand the volume of that box. So the volume goes up, but we still have the same number of molecules at the same temperature, 4 molecules. You can see that those 4 molecules now have a much larger space to roam around. So they're going to run into the sides of the walls a lot less often. They're going to put less pressure against that container. So if volume goes up, pressure goes down. And that's what Boyle's law says, that volume is inversely related to pressure. Now, I want to make sure you understand or have an idea in your mind of what pressure is. Pressure is defined as force per area. So it's the amount of force applied over a certain area. That force could be, for example, in units of newtons. What would be the force of Newton? Newton would be the gravitational force against an apple on the ground, about per area, and that's in area meters squared. That's one example of pressure. Newtons per meter squared is actually defined as a Pascal, P-A. And that's going to be the standard unit of pressure. So that's how you can think of pressure. It's the force of the molecules of gas pushing against the inside of the container. Now let's move on to Charles's law. In Charles's law, if volume increases, then the temperature also increases. All right, let's see if that makes sense. Let's say we have a bunch of molecules in a container, and this container is on a heater. So let's say we have like 3 little molecules, 4 molecules inside that container, and all of a sudden the temperature increases to 2 times the temperature, and we have the same number of molecules, 1, 2, 3, 4, and we would like this gas with 4 molecules to stay at the same pressure. How do we keep it at that constant pressure? Well, we're gonna have to increase the volume to 2 times that volume that we had before, because those 4 molecules of gas, there's the 4th one, that are moving around, now there's a higher temperature, so they're going to be moving around at a faster rate, running into the walls of the container more often, so putting a bigger pressure against the walls of the container. Unless you increase the volume, then those molecules have more room to move around. They're going to hit the sides of the container less often. The pressure will remain constant. So higher temperature means higher volume. Now we have the final law, Avogadro's law. Put an A for his law. And this relates the number of moles to the volume. If you double the moles of gas, for example, you better double the volume of that gas as well in order to keep the pressure and the temperature constant. So let's look at our example. We have a container. That container has 4 molecules, and we want to add 4 more molecules, doubling the number of molecules. We want it to have the same pressure as our other container. If we put it in a small container, there'll be a very high pressure because there's a lot of molecules in there. So we need to have double the size of our other container. Now the pressures are about the same. The space between molecules is about the same. The amount they run into the walls of the container are about the same. Now that we understand how these three laws intuitively make sense, let's look again at our ideal gas law formula. Pressure, P, and we know that as pressure goes up, volume has to go down. So those go on the same side. You might be like, what? Why did these go on the same side? Because if the other side remains constant, let's say it's 1, let's say P equals 1 and V equals 1. So P times V equals 1. But let's say we increase the pressure to 2. Now for PV to equal 1, the volume has to decrease to 0.5, so that 2 times 0.5 still equals 1. And we know from Avogadro's law that as volume goes up, the number of moles also is going to go up. We know according to Charles's law, volume goes up, temperature goes up, they're directly related. PV equals nRT. Now let's use this. Let's look at what values the problem gives us and what values we want to solve for. All right, the problem gives us 0.65 moles. Great, we have our moles, a little in there. Check that off. Occupies 37 degrees Celsius. Now we gotta be careful because in the ideal gas law, you cannot put temperature in degrees Celsius. It must be in Kelvin. So please, please do not make the mistake of just plugging in 37 degrees Celsius into this formula. Don't do it. You must convert it to Kelvin first. So instead of just putting a check mark, I'm going to go ahead and convert to Kelvin right away so that I don't forget later. We'll write our 37 degrees Celsius. And to convert that to Kelvin, you simply add 273.15, 310.15 Kelvin. All right, we have our Kelvin. We know that's one of the things we're going to plug in later. And it asks us to solve for volume. So we're just going to put a question mark over our volume. And it gives us pressure in torr. The unit that they give us for pressure, that's what tells us what value for R we want, what R constant we're looking for. And we can see that the only value of R that has torr in it is in fact the constant 62.3637 liters times torr per mole times Kelvin. So that's our value. Now we know we need to solve for volume, so let's go ahead and get volume by itself on one side of the equation. Just using our letters here, volume equals nRT, and to get P, pressure, to the other side of the equation, we just divide both sides by P. And now we just fill in our values that they gave us. Right, so here we have the values plugged into our formula. Volume equals nRT over pressure. And we just plug in those values that they give us in the equation. Remember, temperature converted into Kelvin equals, and we'll plug that into the calculator. Actually cut that down to 2 significant figures because the 0.65 moles that they gave us only has 2 significant figures, the 6 and the 5, which would just give us 22 liters. Bam! Great job. So let's review what we did. We were given a problem involving an ideal gas where they asked us to solve for volume, and they gave us the number of moles, they gave us the temperature, and they gave us the pressure. Fortunately, we have a formula for this called the ideal gas law, PV equals nRT. We discussed the 3 laws that make up the ideal gas law, Boyles Law, Charles' Law, and Avogadro's Law, and we discussed why these laws make intuitive sense. Then we applied the formula to the problem that they gave us, and we solved for our volume, making sure that we did not insert degrees Celsius into the equation. Kelvin. Great job. See you next time. Bye.